oftentimes we find voids in this space of the possible that there's no reason really of why we don't find equivalences there. And for us, it's been also an opportunity for thinking in, okay, could we, using synthetic biology, try to fill that? There are crazy projects that's still ongoing, is the possibility of implementing, using bacteria, implementing new rules of interaction that made our bacteria behave like ants as in ant colonies. Mm-hmm. Of course, ants use these specific rules of building morphogenetic fields, etc., because then collectively they can solve problems. And in bacteria, you see kind of preconditions of that, cordon sensing, all the things that can be identified in ant colonies, but not the whole story. And you can ask yourself, why is not there? What are the reasons why bacteria don't need to use that or cannot get there? But for us, synthetic biology is a way of interrogating complexity, interrogating evolution. When you try to build, let's say, computational circuits and implement them in cells, I think it's a good lesson for design and evolution. People used to follow the standard electronic design principles. The more cables you put inside, the more, and I can tell, the more easy is that this interferes with something else. So to avoid that, we ended up in a design principle based on multiple cells that do not have to be connected between them. So the principle that we obtain, which we call distributed computation, is not based on standard electronic design, because we can somehow break the circuits into pieces, but it's not in biology. We don't find that in biological systems, which is kind of a good story because it tells us that maybe there are things to discover there that can be part of what we need.
Yeah, I don't know if I ever told you, but we have this project to train an ant colony. Not the individual ants, but the colony. What we wanted to do was to have a machine that there's two areas, A and B. And area 1 just has a camera on it, and it just counts the number of ants on a little platform. That's it. But area B receives food in proportion to how many ants are standing on platform A. So no individual ant would ever have the experience of I do action A and then I receive food at B because it's too far. So no individual ant would have that. But as the collective, I thought, okay, could the colony learn to send a bunch of ants over here so that it could pick up the reward over here, right? Like associative conditioning, but in a distributed way.
What you're saying, it makes sense. Is this work by people from Brussels? They use small robots to interact with cockroaches. The cockroaches do not behave like ants, but you can actually use robots that kind of trick a little bit their interactions so that they end up collectively making decision making. It tells us that the right ways of interfering with the interactions between ants can actually trigger collective dynamics that is what you expect from collective intelligence.
That's a kind of chimera, right? At the population level, we do a lot of that stuff at the level of morphology by combining cells from different species to see how the goals of the collective change when you've got parts that used to be different things. I'll have to look that up. That's very interesting. This kind of distributed learning thing. Do you think we could do something like this in bacteria? Could we use a biofilm and try to show distributed some kind of associative learning that's spread out in space? What do you think about that?
What if we implement that in a multicellular system that has coherence? We were thinking biofilms is one possibility. We're thinking in maybe spheroids. So having a spheroid that is kind of augmented in its potential capabilities by having associative learning, for example, distributed in different cells with that. The nice thing of the model of this is that we have shown that you can have associative learning with short and long memory processing plus forgetting. So the whole spectrum of possibilities is there. It's in the twilight zone between the real biological matter, the organs and organoids, and everything that happens in cell collectives in nature. So again, it's in. I think that it's again for the voids in the morphospace. That's one of the big candidates, and it should be done. It should be doable.
In your synthetic biology approaches, How much do you see that, and do you have any cool examples of the material trying to resist what you're trying to do to it? I mean, there are difficulties, as you've pointed out, that are just sort of passive difficulties of it. But do you see interesting examples of the system resisting the hacking that you're trying to do to trying to get around whatever you're trying to force?
The process of copying and rewiring is extremely extended, and that means that the circuits you have pretty much nothing to do with electronic designs or anything that we are familiar from engineering. Is it possible to somehow interfere with this kind of tinkering process?
As you know, my thinking is that we're going to have to do what we've done for millennia in neuroscience, which is to try to control it top down, incentivizing training. I agree with you. I think this kind of bottom up tinkering is going to be very, very difficult in the long term. We have some opportunities now to discover, do these systems, which I think they do, but to really understand what are the interfaces that they give us for top down control, right? To make them basically, reset the set points and make them motivated in effect to do the kinds of things we want them to do, not to try to micromanage it.